We have already gone through the data section and the BSS section. I think I hope that it is very clear, and if not, I would really request you to go back and revisit the video. That would really help the next topic, and also help you drive things on. Now let's talk about the text section. So text, as the name suggests, has your code residing in it. So whatever code we have, code meaning the C code which we write, which then translates into the assembly instructions. All of those, each and every instruction is placed into your text section. And let's talk about the two environments which we sort of shed the light around last time. First one was the hosted environment, which means that you are running your code on top of a OS, just like our Hello World programs, which have a Linux or a Windows OS, which then hosts the program. So those are hosted environment. Second one are the freestanding environment, which typically has a small microcontroller just executing a bare metal code, which is developed by us in C from the scratch. Okay, so what happens, let's try to see what happens to the text section, where it is and where it gets loaded in both of these environments separately. So
Right.
I think it would be easy to first talk about the free standing environment. Yeah. So there, because we know for sure that our code, let's talk about, you are satisfied with the code, debugging has happened, there are no obvious errors, and the code is functioning as we want it to be. After that point, we are sure that it's not going to change much, in fact at all. So what would make sense is we put it somewhere which does not require frequent updates, and it does not lose its content even if the device or the product is powered off. And the best candidate for that, as we have discussed in the last one, would be the read-only memory, the non-volatile storage, which doesn't lose its content even if it is powered off. So
At this point, I just want to paint more imagination. People can imagine this to be the flash memory. So flash memory, we can actually reprogram it multiple times using an external hardware. But once programmed, so think of this like your USB pen drive, that kind of memory, that you can program it again and again, certain number of times, and every time there is a power reset, the data is not lost.
Right.
So they
that's a beautiful analogy, and I know because you use the USB pen drive as an example. If the astute among you might have tried to make a USB pen drive as bootable, so that's precisely what happens there. The code and all the data needed is stored in the pen drive, and it doesn't mean that you cannot reprogram it. You can reprogram it, but there is hardly the case where it needs to be.
Correct, and it's immune to power cycles.
Yeah,
that is the case.
Right.
So when Mohammed was mentioning that frequent updates are not required, so people usually think of ROM as, okay, once I program it, I cannot reprogram it. Well, true, but then there is flash technology which allows you to reprogram. So ROM updates can be given as well, and the ROM in that case means, hey, it's read only, because the microcontroller itself cannot go and modify the flash memory. An external circuit is required to kind of raise the voltage and burn new bits and all of that. But what people should remember is, for all practical purposes, when we are referring to ROM, we are referring to it as read-only memory, which the code itself cannot go and modify.
Yeah, precisely.
Code resident on the microcontroller cannot go and modify. Okay, go ahead.
Yeah, perfect. So if you recall, the data section also resides in ROM. Again, it is sort of part of your code itself, but there is a small distinction. So for example, our code instruction contains, our code file, let's say it contains int y equals 10, which is global somewhere. Now you can just as well put it, that 10, in the text section also, and therefore eliminating the need of data. But here the distinction is that we know that y is going to be reused and reprogrammed to some other value, and that is different from text, right? So text, your code instructions, the adds, the subtracts, the multiplies, the loads
Hmm.
and stores, all of them, those are never going to change, at least for
Hmm.
the context of that uh, uh, code's life cycle. So
Right.
we can always go back and program via the external hardware. But if we discard that case, your text section is immune to changes. And that is
Right.
where we have this, we don't need a copy of that in our RAM
Hmm.
counterpart, because
Right.
since it is not going to change, we can just as well execute it from ROM and
Yes.
do with it, right? and
Right.
and call it a day, basically.
I got one more reasoning as to why the data, initialized data, for example, should not be within the text region. The reason to that is when our initialization code is wanting to initialize the data section
Hmm.
values in, let's say, the RAM,
Hmm.
well, how is it going to keep track of, which all regions to pick the
Correct, correct,
initialized
correct.
values
Yeah, so you'll have to basically, devise a very prudent logic of maintaining tables and all the
to?
locations. It's just very, very difficult.
Right.
I mean,
So it can be done, but I
done.
think it will come with, again, the table needs to be maintained somewhere.
Right,
That takes memory and all of
right.
that.
And the
So
more
I
fragmented your variables are, the
the
harder it
more
becomes.
yeah, the harder it becomes. So it becomes very straightforward that let's put all the data section or the
Hmm.
initialized globals in one place so that it's easy to copy.
Hmm. Yeah, and here is a small catch. I think I have observed, so let's go to the physical characteristics of ROM and RAM.
Hmm.
ROM, brings the advantages of being non-volatile, immune to power cycle. You can just as well, have storage without having to power it up, right?
Right.
But the disadvantage is they are a little bit slower. And when it's a little
Hmm.
bit, it's very slow in terms of their clock frequencies. And RAMs typically are much faster, sometimes orders of magnitudes faster.
Hmm. Hmm. Hmm.
So when we say the text section is not copied, typically it is the case because there is no need to. But
Hmm.
if, let's say, your system is sort of a little bit more complex and a little bit expensive, in the sense that they can afford more memory, more storage, more memory meaning more DRAM, then what they do is they also copy the text section blindly to RAM, just so they can
Hmm.
access the text with very high speed.
Right.
Occasionally
And
they
what
can
you're
add something.
Yeah, yeah. Well, I just want to kind of call out that what you're talking about is now the hosted environment.
Right. Hosted
Right.
or even in the freestanding environment, I have seen typically
I
that.
see. I see. So I just want to draw some pictures
Hmm,
to suggest what you were doing.
hmm,
So let's say we had slow ROM.
hmm,
So what you're proposing is because the access time here would be slow, it obviously makes sense that we keep our like more reasons to keep the
hmm.
data in the RAM region.
Obviously.
RAMs are
Hmm,
usually more, they're
hmm,
fast. Okay, that's one. The second thing is the processors can actually fetch multiple bytes of the instructions.
hmm.
And that way, they can fetch, let's say, 10 lines of instruction to their own instruction cache.
Yeah.
There's something called, let's say, iCache. Uh, and the CPU is right here. So the CPU
Piyush,
can
maybe
just,
you can draw a little bit
oh,
on.
wow, okay. I keep forgetting
Hmm,
this. So let me draw
hmm,
here. So let's say we have the CPU, which is right here,
hmm,
and then we have the iCache. So what the CPU can do, what the system can do is continue to fetch instructions from the slow ROM to the iCache and then fetch them very fast from the iCache. So while it is executing the first instruction, the second, third, fourth, fifth are already available. And while it is executing those now, it can issue fetch of the further instructions.
right.
So using a cache, that slowness of the ROM in terms of getting the instruction that can be dealt with was
Hmm,
number one. And this is again in the freestanding environment, very useful. Data, however, well, we can have data cache, of course,
right.
but data is something if you choose to modify back to back, X is getting incremented from like 10 to 10,000, then the access is back to back and very fast. and so it helps that your RAM be faster than the ROM. Number one.
Hmm.
Now, what you were alluding to is, so I just want to draw that kind of line, or just to make it more clear, because okay, let's first talk about the extreme poles and then the combination in between. Right? So what you were hinting at was, let's say if you have the hard disk, which is a ROM per se, where your program is saved,
Right.
and if you want to execute that, then of course the DRAM on your computer systems, for
Hmm.
example, some part of that will be treated like a data section.
Hmm. Hmm.
And then what can happen is, because fetching the instructions is also terribly slow, to the point like HDD is very slow than
Yeah.
EEPROM and things
Some
like that,
10,000 times slower than.
right? Orders of magnitude
Yeah.
slower. So it makes sense that you, oh wow, I just lost connection. Just a moment.
Yeah.
What is happening? Okay. All sort of amazing things. Okay. So what I was mentioning was, okay, because the fetch is so slow,
Hmm.
what the OS tends to do is also keep chunks of your program
Hmm.
in the RAM. What is happening? Okay, I have no idea. Okay, so it can keep chunks of your RAM, chunks of your program in the
Hmm.
RAM. And now all of a sudden, if people are getting confused, well, hang on, because when we come to the topic of MMU,
Hmm.
virtual memory, how operating systems work, then what we learn is that the operating system guards this
Yeah.
region as read only, even though it is in RAM.
Right.
So this is for the case of operating systems
Hmm.
where the program is loaded from hard disk to the RAM.
Hmm.
Your
And
data,
sorry,
go ahead, go ahead.
for our audience, if we are, jumping up a lot, and
Yeah,
we are sort of segueing into a lot many topics, but
yes,
this is our intention to clarify when we had made the earlier statement that the text section only resides in read-only or non-volatile storage. So you
correct,
also wanted to cover these aspects where it might not be the case. And
correct.
the reason would be that if someone asks, like, hey, can you think of scenarios where it might not be true? So we want you to be equipped to answer
Able
those.
to, yeah, reason around that. And again, when I was mentioning, let's talk about the true extreme.
Hmm.
Well, in this case, you have the text section in the DRAM, where
Right.
the text section is guarded by the, so well, it's guarded somehow by the operating system to be
Hmm.
a read only.
Hmm.
So the program cannot go ahead and modify itself.
Modify.
Right? So that is like self modification is not allowed.
Hmm.
And the other extreme is where the text section only resides in the ROM, but that's in the freestanding case.
Hmm. Hmm.
That's on the microcontroller
Yeah.
targets. So we wanted you to be able to understand how the memory layouts are for a given program, and then reason as to how it would be in the freestanding environment, how it would be in the OS
Hmm.
environment. And then obviously, there's no hard and fast rule in engineering. So if you, for whatever reason, had a reason for having a self-modifying code, well, then you could somehow work with the operating system to have this region as read write,
Yeah.
and then the code can also be modified.
Right. And in
If
fact, this is what the attack surface. This is where the attack surface is open up for this Trojan and all of
yes, Trojan horse,
that.
viruses, and all of that, they tend to kind of leverage
Yeah.
compromising the security by essentially messing up with the operating
Hmm.
system. Right? Okay, I think so. This one was good enough in terms of talking about the text section and where all it is laid out. We also wanted to talk about the stack section, but I think that's a good topic for next lecture.
Yeah.
We can cover stack and heap.
Right. Right.
All right. So with that, we'll see you in the next one.